Be it the search engine that we use every day for our queries, or the VPN that enable us to work from the comfort of our home, or the cloud that we use to store our files. Internet is an inseparable part of our lives. But if not cautious, it can compromise our privacy, identity, and even financial security. Hence, it is crucial to protect ourselves from these threats, right? So, this brings us to the topic of discussion Trojan NIDS, a SNORT offloader developed by Team.bit. But before we dig deeper, it is important to consider a scenario that elaborates why these systems are important and how they can save the day. This helps us justify the cost and effort that was put into designing such a system. A disclaimer before you go, all characters here are purely fictional.
Hey, this is Kim.
Hey, this is Joe. Joe Mama.
Hello, I'm Agent X.
I want to install malware on Jay's computer to steal the Rackadown's code. It's Joe's birthday today. Let me send him a happy birthday email with a phishing link.
How sweet of Kim. He wished me happy birthday and sent a link to cat videos. Let me watch the cat videos he has sent.
I have the rocket launch code snippet of new I lost connection.
So we can see that not everyone is as lucky as Joe. So the world almost lost $10 trillion annually due to cybercrime.
Sir, we just had a network intrusion.
How is that possible? I have a firewall installed on my device.
So what does a firewall do? The firewall just checks the header of the packet. It doesn't check the whole packet. It doesn't do deep packet inspection. So let us take an example of a packet with a good looking header and a malicious payload. So it goes to the firewall, gets the green flag, goes to the system, it creates havoc. Okay, so how does IDS and IPS work? So it goes to IPS, IDS, there's a deep packet inspection, the packet is dropped and the system is secure.
Thank God we have an IDSPS. What in IDSPS are we using?
We are using SNORT.
So what is SNORT? SNORT is a powerful and a versatile industry standard network intrusion detection system. It performs deep packet inspection and provides greater control in detecting malicious activities. We specify SNORT rules to tell the SNORT about malicious packets. There are about 50,000 plus SNORT signatures that are updated regularly.
But there is a problem, Agent X.
What problem, sir?
I am having bandwidth issues.
This is one of the drawbacks of the software SNORT.
So these are some more drawbacks of software SNORT, like resource utilization, limited visibility, and vulnerabilities.
What is the solution?
We are upgrading our systems to Trojan nets.
So, what exactly is Trojan Network Intrusion Detection System? So, the Trojan Network Intrusion Detection System is a hardware accelerated deep packet inspector. To be more precise, what it does is basically it accelerates the software snort that is there. So that acts as a so just like your GPU accelerates a matrix operations for your CPU, this Trojan NIDS accelerates the snort processing for all of your networking applications, right? So it does so by offloading some of the work the sister node, right? So what it does is as soon as the packet starts coming in, there is a hardware accelerator pattern matching block that is inside this. So that keeps on checking if there is any match, and if there is a possible match, it won't completely determine if the pattern is there or not. It'll just send that particular packet to the next node, the sister node that is sitting there, right? Or else most of the packets where you don't have the probability of having the any signatures or any patterns, they'll be sent directly through. So that is why it accelerates them, since it does that in hardware. right, rather than doing it in software, which is very dense code. And then because it's able to do it at very fast rate, the throughput is also very high, and it is able to support processing at gigabit line rates, right? So so this is what is the main component, the control node, right? So this is the Linux server. On top of it, the net FPGA sits on it with 4 Ethernet ports and also 4 uh, PCIe CPU queues, right? So let's see what's inside this net FPGA. So net FPGA is loaded with a reference router bit file, but we have modified that. So there are the usual blocks like input queue, output port lookup, output port queues and stuff. But there are 2 other blocks that is where the magic happens. So one is the pattern matcher block and other one is the multi-core block. So this is where really the stuff that accelerates all this NOT goes on, right? So let's see how it works. So let's start with the packet. So the packet is coming from the upper block, the upstream registers that are there. So the packet first comes and that gets stored in the FIFO of the pattern matcher block, right? That transfers that packet to all the Bloom filters, right? So there are multiple Bloom filters because there are multiple multi-bit patterns, right? Multi-byte patterns, right? So for example, for one particular Bloom filter block for 3-byte pattern, one particular Bloom filter block for 4-byte pattern, another one for 5-byte pattern, and so on, right? So the packet is sent parallelly to all of them, right? Now, within certain clock cycles, which we will see, it'll get updated, right? So we'll get to know if the packet is good to go or not. So the Bloom filter has determined that the packet is good to go. That means it does not have any of the matches. So it lets it go. Next, it comes to the multi-core block, right? So this is where the processing happens. So right now, for those packets which do not have any match, we are not doing any processing. We're just letting it pass through. But if you want, you can do other options like encryption, or if you want to give prioritized access and stuff. So if you can do a whole lot of processing there. Now, simultaneously, another packet arrives in the pattern matcher block. So that is stored in FIFO, and that is also sent to the Bloom filter block there. So now the Bloom filter block says red. That means it says there might be a signature, right? We don't know that yet because of the false positive cases, right? So that packet comes here. So there's a field, separate field along with in data, in control and stuff. So that is called match, in underscore match. So that is a separate interface that is given to the multi-core block, right? So now that comes through the dispatch unit, it goes to the core number 2 because in core number 1, another packet is already being processed, right? So this is how the multi-core processes things, right? Now the packet 1 is done, it goes to the original intended destination, right? Whereas let's see what happens with packet 2, right? Because matcher underscore enable was true for this, that means there is a possibility of pattern. It is sent to the sister node, right? For where the actual software SNORT runs, right? So that is where the processing happens. And what we are doing here is we'll change the output queue in the net FPGA header, and we have to modify the MAC address also, and then we will send it to the sister node, which is N0 in our case, where we will explain the topology in the future slides, right? Now let's see what's inside this pattern matcher. So as I told you, it contains different sets of Bloom filter blocks itself, apart from the FIFO block, right? So the FIFO, it reads all the packets, it reads one packet at a time, and it stores all the words of that packet, and it gives the read pointer and depth information to the Bloom filter blocks. So why this is required is that so when we are checking for pattern, we have to shift it by so we have to check it for byte offset things, right? So we have to offset it by 1 byte at a time and then check for the patterns. So at that time, read pointer and depth becomes very important, right? And also all of these blocks will be done at different times, right? So you have to keep track of all those things too. So that is all done by a finite state machine that is built around these, right? So now here, for example, let's look at how exactly the pattern matching happens for 3 bytes Bloom filter, right? So as you can see, since the pattern we are searching for is 3 bytes, but our actual word is 8 byte 8 byte, ignoring the control fields, right? So we have to check for byte of we have to check for the pattern with each byte offset. So corresponding to that, for a if you want to search for a 3 byte word, you get you have to perform 8 of these operations parallelly, right? I mean, you can do it sequentially also, but if you do it parallelly, it makes more sense, because since you're trying to accelerate things here, right? So we have that. So that is that each of these green, 3 byte, a window of the input. So that is given as the input, right? So that is X. That is what we assume X in the upcoming slides, right? So what hash function does is it takes this. So X, so basically it maps from one universe or one set to another set, which is smaller, right? It maps from a universe U to another, like let's say universe S, which is much smaller compared to U, right? So the kind of hashing function we have used is, so what we do is we basically take the input, every bit of input, we multiply it with a 12-bit number, random 12-bit numbers. I mean, the 12-bit numbers that are randomly chosen, and then at the end we XOR all of them. So that is indicated here. Hi of X is so this is 0th bit of input, X, the first bit, and then it goes on till 24th bit, right? Because this is 3 byte. So 3 byte window we are checking. And then this is DI0, DI1, DI, and then goes on to DI23. So DI is a set of, as I told you, randomly chosen 12-bit values. So totally there are 24 of them, right? So for example, DI0 might be like 001, something like that. It goes on till 12th bit, and so on, right? So hash function takes that input, and then it takes one set of DI, and then it gives you some value, right? So we have made it such that the reason we are taking 12-bit here is because we are choosing the hash array, sorry, the Bloom array to be 4096 bits wide, right? So when you do the XOR operations of all of those, you will get, since all of them will be 12 bits wide, so you'll get 12 bits again. So what we are using is, what we're doing is we are having a dual port memory block, and then we are, indexing these values, right? So it's as soon as we get the hash function, we use that hash function to index into the Bloom array and check if the corresponding bit, the bit is set at that location. So if the bit is set at that location, then probably the pattern might be there. So this is totally we are using 6 hash functions, which I'll be explaining in the future slides. So only if all of those positions are true, I mean, if you get one in all of those positions, only then there might be a possibility of pattern being present, right? So I'm using 6 hash functions because that is going to reduce the false probability a lot, right? So again, since this is a very big operation, I have constructed a very simple pipeline out of this. The first stage, you get the input, the 3 byte window input, and then you have the corresponding set of D0, D1, D2, D3, D4, D5, and then you perform the multiplication operation. So the multiplication operation is very simple. We need not perform the actual, we need not build the booth multiplier and stuff. So for example, you have a 12-bit D0, let's say one of the values, and then so you can just put a mux. We can have a mux there, because if X0, that is the bit, some bit of the X input, if that is 0, then the value will be 0, right? So only if that is 1, then we directly propagate the value of whatever the D is. So we can just put a mux. So it's an optimized function, to be honest. Okay. And then for some values where we can optimize it even more. So that's what I meant to say, right? And then all of these values are computed. So 24 values for one particular set of D, and then all of those values are XORed in the second stage here, right? And then out of these you are getting H0. So this is, out of this you're getting H0, out of this you're getting H1, out of this you're getting H2, H3, H4, and H5. So I have 3 partial Bloom filters. So as I told you, that partial Bloom filter is nothing but it contains the Bloom array, which is 4096 bits wide, 4096 bit deep and 1 bit wide, right? So they are dual port memories basically. And then only if all of them, so when we index into those arrays, we'll get 1 or 0 depending on how we have trained the Bloom array, right? If we happen to get 1 in all of these, only then I'll say match underscore I is 1. That means probably it is true. Still there is a possibility of false positives. So according to our calculation, for if we fill more than 230 signatures for this, for each of these places, each of these arrays, if we fill more than 230 signatures, the false positive probability is going to be around 10.72. So that is the calculation we came across. And some papers talk about 10, 16 hash functions, but we could get the false positivity rate to be optimal around 6, right? So and again, so that was for 1 byte offset, right? So that was for one input 3 byte input window, right? So we had 8 such windows, so we'll compute all of them parallelly and then we OR them, right? So it can be in either of these windows, the pattern can be, right? So we just OR them and then we give it as match. So this is the match for 3 byte one. Similarly, we have the procedures for 4 byte one. Only thing that changes is the apart from the window sizes, the D values that are there, right? So the how many set of for example, here it was set of 24 12-bit values, but when you're considering 4, it is set of 32 12-bit inputs, right? So that is how it happens. So I'll be showing a Verilog code of that, right? And then when we come to processor block, it basically is a dual core quad threaded processor that supports RV64I instruction, which with dispatch unit and issue unit there. So mainly what dispatch unit does is, as soon as the packet comes, it transfers to one of the cores which is free, right? So it's like an arbiter. So for example, both of the cores are empty. The first packet comes, it just pushes it to core 1, and then the next packet comes. If core 1 is busy, it will automatically route it to core 2. So that does same thing with issue unit. Whichever processor is done, just takes the processor underscore done signal from them, and then and then gives the control out data accordingly, so that the packets can be routed out of the net FPGA, right? So that is there. And then the data memory of the data cache of all these processors are basically FIFOs in themselves. So at a time, so they have a finite state machine built around them to do that. So that's inside the processor block. So mainly we use processor block to modify the contents, right? So whenever we get the match to be 1, that means probably the pattern is there. At that time, we use the processor block to modify the NetFPGA module header, which is output queue number, right? So there we modify it so that it goes to the sister node. And also we also change some of the bit fields in the header, right? Some of the header fields we also change that. So that is mainly the job of processor. We can also do, as I mentioned earlier, we can also do other networking applications with this.
Now, we just discussed a lot about the control node, how it works. So we'll now discuss about the sister node SNORT, which runs software SNORT. So this is the topology we propose. First of all, we have 2 lines, right? We have the red lines and the blue lines. So I would run you through what is the significance of it and how it works. So basically, let us assume we get a packet on the control node. and it goes through a net FPGA and there is no pattern match. So basically this packet is intended to go to N1. So the packet, the control node will send this packet on the direct interface to node N1. So let us see how it goes. It just flies down through the interface and go to N1 on the blue interface. So next we look at the second case where the packet, uh, where a packet which is destined to N1 comes to control and is flagged by our hardware uh, accelerated pattern matcher. Next, this packet will be routed through the SNOT. So of course, we'll be setting all the forwarding rules using using the route functionality. Next, it goes to the software SNOT. Here, the packet is checked. So this packet, once it reaches the SNOT, if I and this packet is matched in the SNOT 2, this would be dropped. So next, this packet just goes. So it just gets dropped. The third instance being we get a packet on control. It is flagged by control. And this packet is again destined to N1. It goes to the software SNOT on the red interface. All the flagged packets would travel on the red interface. So this from the software SNOT finds there is no signature match. So it will change the red packet into a green packet and sends it down the red interface. So you can see that the red packet is converted to the green packet and is sent to the switch. This switch will send this packet to N1 on a different interface. So this packet flows and again it flows to N1. Next, we'll discuss how we are running SNOT. We are running SNOT in AF packet mode. We have bridged the two interfaces. If we go according to our example here, we have bridged the interface 10.1.0.3 and 10.1.4.2. So it is in a bridge mode, and our control node, when there is a match, the RISC processor modifies the net FPGA header such that when there is a match, the packet always goes out on the destination port connected to the node N0. Next, we will look at our dashboard. So what is this dashboard we are talking about? So basically, when we were trying to configure everything on SNOT and look at the logs, it really became messy. Like there was no certain way of representing data. So I think for us it was very important to represent the data in a very good way, and we came up with this idea to create a web server where we can show all the logs of what kind of intrusions we had or what kind of alerts or drops we did. So basically, we have the software not running on Node and not, and we have a Python server running on Node and not itself. So what the Python server does, it is that it scans this log continuously, and whenever there is a new log inputted into this log file, it picks up that data and puts it to the MongoDB database, which is there on Node and not itself. The second part of the UI of the dashboard is the UI, which is the Flash server. We have designed this. So this UI was designed using the Python Flash server. So what this web server basically does is it picks up data from the MongoDB database and it shows it in a very presentable manner on a web page. So now we will look at the web page dashboard. So this is our dashboard. So here the data is represented in a very neat manner. The message being the message we set in the SNOT rules, the action, what action was taken for the packet. We have all the destination and source IP and port numbers. We have the protocol for which this happened and the date and the timestamp. So now let us look into our implementation of Trojan IPS. This is the control node where we have loaded our hardware implementation of Trojan IPS, being the Bloom filtered hardware accelerated RISC processor. This is node N0, where we are running the software SNORT, which we use to offload the packets. Next is the two instances of node N1. You might be wondering why I am running two instances of node N1. Here, the node N1 is first of all connected to two interfaces, ETH4 and ETH1. So what are the significance of these? The control node is directly connected to the ETH4 interface. So the packets which do not have a match can directly flow down to the ETH4 interface, while the packets which might have a match or has full match will be again sent to the software SNOT to be verified. If the software SNOT thinks that there is no signature matching, it will forward the packet to the rightful owner N1 on interface ETH1. So coming to our Bloom filter implementation, our Bloom filter is capable of fully matching patterns of width 3 byte to 7 byte wide. And when the pattern is greater than 7 byte wide, which is more than 8 or 8 byte wide, we just do the prefix matching and we leave the rest to be handled by the software SNOT. And one of our major implementations would be our dashboard. You might be wondering, what is a dashboard? So the dashboard consists of two major parts, one being the server, which takes the information from the logs of the software SNOT, and it feeds it to a database. Here we have used a MongoDB. So the second part would be the UI. So you would be asking, where is the UI? So I just show the UI now. So here is the UI. So this is our dashboard. The dashboard basically takes the data from the database and shows it on a web page. So why is the dashboard so useful? So dashboard is very useful for a administrator like Agent X, who's always keeping an eye on the network activity in his premises. So he can be aware of any attacks, like how Kim attacked Joe, or how Kim intended to attack Joe, and those attacks were taken care of by a software SNOT. But here we'll show how our hardware SNOT works hand in hand with the software SNOT to give a better performance. Now let us just come back and look at our implementation. So when I was talking about the pattern width, I said we start with a 3 byte wide pattern. So the first 3 byte wide pattern is .id. So I would be sending a UDP packet with the content .id to node N1. And we will just see how our system reacts to this. Now I've triggered it. So it did go. And I think you saw a fluttering screen onto your right. So here it was logged in our primitive server. This primitive server in turn updates it to the database, and the same information could be viewed on our dashboard. This is the dashboard which keeps on updating. I think if we can keep an eye on the entries in the future. I'll just come back to this page after some while. Now, as of now, there are 17 entries in the table. So now this, you can see this packet.id was not delivered. So the the pattern which was matched and the packet was dropped and it was not delivered to the end node. Sorry, guys, we had to come back. I think there was a problem. The terminal just froze. So I'll just try to do it again. So yeah, see, this was a good pattern. It just flowed right down, and uh, we got the packet here on ETH4. And next, uh, we would look at our 4-byte wide pattern .exe. This could be malicious, right? There could be a malware with an exe and it could easily install on your system. So now let us look at our .exe malware and how it would behave. I would call it malware. So I send the exe file here. So I've triggered it. We see that none of them are received. Oh, okay. I think ETH1 is not running. Okay. I'll do it again, or I send the exe again. It did not come on anyone, and we see some flickering screen on the right again. So the server took the exe pattern, so the software SNORT detected it and it dropped the packet. And now let us again go to our dashboard. So here on the dashboard, we see the increase in entries. There are 19 entries, and we are having the log here on the top. It says UDP detected for pattern.exe and the action was dropped. We have all the information like the source and destination IP and port, the protocol, the time, and the date. So this is very good information and it could be used for further actions. Now, again, let us come back to our very old terminal. Next would be our 7-byte wide pattern. The 7-byte wide pattern being WAIS.pl. Okay, sounds fancy. This is right off the SNORT rules. The WAIS.pl is one of the kind of packets which you would like to drop. So these are from the SNORT community rules. So I would just do the same thing. I would just, instead of our exe, which is REDful, I would send this WAIS.pl packet. Now let us see how it behaves. So when I do this, WAIS.pl, I'll trigger this. So we don't see any dump. So and it is again recorded by a software SNORT, and a quick flip of pages here. We had reloaded. I think there was a problem. Okay, see, we have WAIS.pl here updated on our table. Coming back. Next would be our pattern, which would just do prefix matching, which would be ppdscgi.exe. Here I would be sending ppdsgi.exe. I think our implementation would just be limited to the top 7 bytes of this pattern. So I'll just put this pattern here, and even our SNORT is configured to drop this packet. Let us see what happens. Yeah, the SNORT detected the .exe. Okay, and the SNORT has another rule to drop the same packet but with an extension DLL. Okay, let us try this too. SNORT, yes, the SNORT detected this. I think it would be much better to view it on the dashboard here. So here UDP detected for pattern.dll and it was dropped. Next, we'll go back to our terminal. The last would be the same thing, but it wouldn't be dropped. I think we'll change the extension to something which is not there configured on our rules or not trained on our Bloom filter. We'll just do ABC. Let us see what happens. Hope the terminal is not frozen. Yes, it is not. And it has gone through the SNORT has flagged it green, and we have come down on ETH1. So here I would like to stop the demo. So we have covered all the type of patterns, not all of them, but some of them which we have covered, and we have explained how our implementation works. And for the ease of the explanation, I've just used node N1. All of these do hold true for node N2 and N3 too.
Now this is the throughput analysis. The throughput analysis compares three methods, and we are using the iPerf to measure the throughput performance. For the dark blue one, this is the without SNORT. We just download the reference router design on the NetFPGA, and the throughput is about 940 megabits per second. And for the only SNORT one method, we download the reference router on NetFPGA, and we also run the software SNORT on the control node. So the throughput drops to about 600 megabits per second. And the light green one, which is our method, we offload the packets to N0 with the help of our hardware in the NetFPGA. So the throughput increased back to about 850, and the increment is 260 megabits per second. So it's about like 45%. And now this is the cost analysis with respect to the network performance. There are three NetFPGA shown in here. We Google it the cost of on the internet, and for the NetFPGA Plus, it uses two 100 gigabits Ethernet port, and the SUME port, it uses 410 gigabits, and the 1 gigabit NetFPGA 1G, which is used in our experiment, it is for 1 gigabit bidirectional port, so it has 8 gigabit throughput. And we have calculated the throughput increase per dollar as shown in here, and these two are the estimated throughput increases because we don't have that board, and this value is calculated by divide by the throughput increase, which is like 260 divided to the 1499, so it's about like 0.18.
Just to make the explanation regarding the hash arrays and Bloom filters more clearer, I'm showing the RTL implementation here. So the partial Bloom filter that we discussed is nothing but a dual port memory block that you can see here, right? So that is 1 bit wide and 4096 in depth. So that is fixed for all the blocks. So as we saw in slides, let's talk about the 3-byte Bloom filter, right? So for recognizing 3-byte windows patterns, I mean. Right, so we looked at the partial Bloom filter. Partial Bloom filter will be same for all the blocks, basically, whether it's 4 bytes, 5 bytes and stuff. So only thing that happens is that as you go on increasing, so as you go on to 7 bytes and stuff, so you cannot fit in a lot of signatures basically in the same hash array. You will get a lot of false positive rates, right? So we would want to keep it below 10%. So that is the thing. So that is the thing about partial Bloom filter. Now this is the hash array. So this basically takes the input X. So as you can see that 3-byte window that we talked about, so that it takes, and then it takes the DI, right? So it's a set of 24 12-bit data basically. So that is the thing. So from here D0 to D23, right? So that is stored here, right? So for example, this is for generating H0 hash 0. So this is the set of 12-bit integers we have chosen. So these are chosen at random, okay, to ensure that the uniformity of the function is preserved, right? So this is for generating H1. So and this will be used for calculating H2, sorry, and then this is H for H3, and then this is for H4, and then this is for H5, right? So you can see those values are hard coded here. So before that we were so we'll instantiate these hash arrays here. At that time I'm hard coding them, so I'll talk about that a little later. But assume for now I'm already getting these D values, that is the 12-bit values as input, right? So how are we calculating the intermediate variables? That is the multiplication, right? So as I mentioned earlier, we can use a mux. So as you can see here, depending on the 0th bit of X, so if it's 0, I can directly assign it to 0, right? The output. right? Or else I can just if it's 1, I can just directly pass away d0. So that's how I'm doing multiplication. I figured out this is much more efficient, to do. Another possible optimization is to use AND gates and stuff, so that is there, but since we had scarcity of time, we couldn't do that, right? And then I'm talking about stage registers here. The first, I'm calculating the multiplication intermediates, right? So that I'm doing, and after that, at the second stage, I am doing the XOR operation of all of those, right? 24 values, right? So that is going to give my hash value, right? For example, if I'm using x and d0, this will be hash 0, h0, and if I'm using x and let's say d1, so this will be h1, and so on, right? So that is calculated here, right? So each Bloom filter is since it's a dual port memory, I'm taking input from 2 hashes to check if the if to check for the presence of pattern, basically, like after the training phase, right? So you can see hash array a0 and a1. So I'm hard coding these values that are that is the 24 number of 12-bit values that I'm hard coding here, right? So that is there, and then I'm giving the h0 h1 here, and that is I'm getting r0 r1 here. I'm again using that in a pipeline to get the match here, right? So the match is true only if all of those values are true. That means I take an input and then I hash with different functions, and then I find one at all of the locations pointed to by them in different Bloom filters. If that is true, then that's definitely a match. So before that, obviously it goes through a phase of training, right? So for that, what we did was we basically loaded the coefficient file itself to the memory based on whatever rules we wanted to support from the SNORT. We based on those, we wrote a Python script to calculate the hash values and the corresponding a coefficient file for that. And so for example, you can see these, it's mostly 0, I think somewhere it's very hard to see, but you will get ones. So that is basically how we did it, and then we initialize that so that we don't need to train the Bloom filter, right? So when we initialize it, it's already trained using coefficient files, right? And then from that so that is there, and then these are the byte offset shifters, right? So for example, I'm instantiating all of them with byte offset of the words. So you can see the first 4 bytes, I'm just the first 3 bytes, I'm just giving it to the first one. Next, I'm shifting it by 1 byte, and so on. And next word also comes into picture, right, to accommodate for all the possibilities. And then if any of them is 1, then the match is there, right? So we ran the simulation, and then one of the bits for which we had trained are this thing, Bloom filter. So that was that is 646060, right? So that is the DLL. So if we send that in the input, we can notice the match is enabled here, and then we are giving another interface called match that goes on to the processor block. So that will be high if we found a match for the entire section of the word, the output, right? Sorry, the packet, right? So I wanted it specifically like that because in the process stage, I had built a finite state machine where in the execution, after the execution stage, right before the execution stage, the matcher gets stored to the one of the register files in the processor, so that to enable processing, basically. So that's why I want it high all the way around. So throughout the way. So that's the thing. But here I'm sending some input without any pattern, right? So let's see what that does. I think this should be enough. Yeah, you can see out data and out control we're getting here, but there is no match, right? So that is how kind of how it works.